someone. Where's Alexis?
She's right here.
Oh, she's here? Okay.
Hola.
All right, so let's talk about BMS. So BMS stands for the Battery Management System, and it's what we have in the car to basically monitor the voltage and temperature of the batteries and take care of the charging and communicate all the necessary information to the VCU, which is what's hooked up to the inverter and controlling the speed of the car, and also sending data to the dashboard for our data acquisition to record this and review it afterwards. So on the voltage reading side, we have 4 BMS slaves, and these are, I can actually show it to you. I have it here. So we have 4 of these PCBs. Not sure if you can see it.
How do
So
we
have
make you bigger?
How do you?
I don't know.
Works enough. Or, oh wait, no, if you close the call it won't be recording.
What?
Will
Oh.
will it work that way? Anyway, just keep going.
Yeah, so anyway, we have 4 of these hooked up to the BMS master, and each one of these is connected to a pack of 10 cells or 10 batteries in series, and each one is 10 cells in parallel with each other. And each one is also reading the temperatures of 8 cells. And so if you can see, like, from, I guess it's not really important, but yeah, it's connected to each one of these batteries, and they're connected to each other in something called a daisy chain, which basically means that sorry, could one of you mute their mic? It's kind of loud. Thanks. Daisy chain means that you can just communicate with the first board on the stack, and it will actually forward this message to the other BMS slaves. So you don't need to be individually communicating with each one. You can just be communicating with one, and it'll forward those messages. Do you guys have any questions on this part? All right, so because we only have 32 temperature measurements that we can do with the BMS slaves, we needed to make something called the thermistor expansion boards, because we're mandated by the rules to be reading a certain percentage of our cells. And so what this is basically 96 thermistors that are connected to each individual cell. And based on the temperature of the cell, we're getting different readings. And so this is just a pretty basic PCB, just reading analog values and sending it to the BMS master. Any questions about this part? All right. And then we have the charger. So the charger actually works, or the software behind the charger works in conjunction with the BMS slaves, because this is controlling how much, the BMS master is controlling how much the charger allows current and voltage to go to the battery pack. And so the BMS master is balancing the cells as we're charging the pack, because we have 400 cells, and so they're all based on their different factors. They're going to charge at slightly different rates, and so you end up with some cells charging a little faster, which can cause problems if one of them hits over voltage before the other cells, because then you won't be getting the full capacity out of your battery. And so the BMS master, during the charging process, it's sending CAN messages to the charger, and it's also reading back the voltages and seeing which cells it needs to balance. And when I say balance, I mean it basically takes the cell that's higher voltage than the other cells and allows less current to go into that cell. So it will charge slower. And so that's the gist of the charging process. Do you guys have any questions about this?
So to clarify, how we'd actually balance these cells is through the charger. Like where these the current is coming from is from the charger.
No, so you'll be still sending the same current and voltage through the charger,
Uh
but the BMS the BMS slaves itself. Oh, it's like filtering it out.
huh.
How do I remove the backgrounds?
You set it up, man. I don't know how you do that.
Okay. The BMS slave actually has basically bypass lines through each cells, and that just means that it'll add an extra resistor at the line where the cell is and have the actual cell taking in less current. The
Oh.
charger will be sending the same like voltage and current, but the BMS slaves are just discharging some of that current in the form of heat in a resistor.
Oh.
And this is called passive cell balancing, where you just basically like remove some of the current through a resistor as heat, which is what we do here because it's a lot simpler than active cell balancing, where you actually take the cell that's at a higher voltage and route its current to the cell at a lower voltage. So then you're not wasting any power.
Mhm.
But that's more complicated. And the chip we're using is more suited for passive. So that's what we went with.
Yeah, one of you guys will do active in the future.
Yeah, that'd be sick.
Be more
Um,
powerful.
all right. I want to start hearing questions.
3 questions, go.
Yeah.
Now
Because
progress.
like if
Yeah.
this was explained to me with no knowledge about it, I would not be understanding anything. So like I want you guys to get a really good understanding about the BMS master and how it works. So even if it's something simple, don't be afraid to ask.
How does your daisy? Oh, go ahead. No, you. Okay. Can you please elaborate on how balancing works exactly?
Mm-hmm. Let me see if we had a handy diagram before. It's not here. Let's Google it.
I'm sorry I cut you off on that.
No, that's fine. I want you guys to really understand it. So
It's a
this
battle for
exactly is what I'm
questions.
talking about. So you have, if you look at it, you have the cells that are being charged. And let's say the current is flowing this way and charging these cells. And so for example, if cell 2 is at a higher voltage than cell 1, and we want to just slow down its charging a bit, slow down how much current it's getting, the BMS master would send the signal to close switch 2, and this means that some of the current is going to be flowing through the cell, but then some of the current is also going to be flowing through the resistor. And so the cell is not going to be getting all that current, and so it's going to be charging at a slightly slower rate than cell 1 and 3. And so the BMS master is constantly reading the voltages of the cells and deciding which switches it wants to close based on the differences in their voltages.
So like if it's charging and one cell is charging faster than the other cell, the switch would turn on and that would slow down that faster cell, right?
Because if
Okay.
you remember, like the way current works when you have parallel lines, the current is gonna come in here, and then it's gonna split into cell 2 and into R2. And so cell 2 is not gonna be getting as much current anymore. So it's gonna, and current is really what's controlling how fast the cell is charging. It's gonna charge at a slower rate.
Okay. And like in the balancing process, like can we like drain the batteries? Like I'm not sure how it works, but like
So that would be active cell balancing,
okay,
where
that
you
also exists. Okay.
take the current, like yeah, if you in active cell balancing, if cell 2 had a higher voltage than cell 1, you would route some of its current to cell 1 instead of just wasting it on the resistor. But then that's more complicated, so passive cell balancing, you just need to be controlling some switches, and we don't really care about efficiency that much. And so this works for what we're trying to do. Does that explain it for you? Oh, sorry. Go ahead, Emma.
Why is it important to balance the cells? So, like, why are we trying to charge them at the same rate?
Great question. So a lithium ion cell basically has a usable range from 3.2 volts to 4.2 volts. And any higher than 4.2 volts, and you get to a state that's called over voltage, and it's actually dangerous. The cell has too much energy, and in some cases, if you keep overcharging it, it can catch on fire because it's not stable anymore outside that voltage range. And so if cell 2 has been consistently charging at a higher rate and it reaches 4.2 volts, but cell 1 and cell 3 are still at 4 volts, then cell 2 is still going to keep charging because current is still passing through it. So it's just going to keep going higher and higher, while cell 1 and cell 3 are still under the threshold that we want to reach, because we want to reach that every cell is at 4.2 to be using the full capacity of the battery. And there's no way to just like stop charging completely a specific cell, because if you like if you cut the line from cell 2, then you're breaking the circuit and the current's not flowing through the whole battery pack. And so the best way to tackle this is to, while you're charging, don't let the differences become so big, and just as the differences are in millivolts, you keep switching like S2 on and S1 off and S3 on, just to keep them going up at the same rate. Does that help explain it?
Yeah, that makes sense.
Cool. Alexis, do you have any questions?
You mentioned something somewhere else, unrelated to this, of high voltage to low voltage. Is that always like a case where you would go from high voltage to low voltage and not low voltage to high voltage?
I'm not sure what you're talking about, to be honest.
I don't know. You
High
mentioned
voltage to low voltage.
and I was just a little confused, but I don't remember where you mentioned it.
Do you guys remember if I talked about high voltage to low voltage or that stuff?
In what context are you thinking of, Alexis?
I'm not sure. I forget.
Like, what's confusing about high voltage / low voltage?
Well, my question was like, would you always go from a high voltage to a low voltage, or could you interchange the two, where you go from a low voltage to a high voltage?
Oh, I think I get what you're asking. Like when I was talking about active cell balancing,
Yeah.
and you take the route the current from the higher voltage cell to the lower voltage cell. That would, yeah, you'd always be doing that for active cell balancing
Okay.
because you don't want to charge the cell that's at a higher voltage at an even higher rate. But we don't use that. We don't use active balancing anyway. We just use passive balancing, which just routes some of the current to a resistor if we want to slow down the charging rates.
Okay.
So do you kind of get what I mean when do you get kind of what passive balancing means now?
A little bit. I understand that you would close the switch and then it would allow the other cells to charge faster.
It's kind of like, I guess the way to explain it is if you have like 3 guys running a race and one of them is running too fast, and so you put some weights on him so he runs a little slower. Because if you want, for some reason, this race, the goal is to have them run at the same pace. And so you put some weights on the guy that's running too fast so he runs a little slower. This
Yeah.
is exactly what we're doing,
Excellent.
putting a resistor. And that slows down the charging of the cell.
Okay.
Mhm.
Oh, you know what? It makes sense if all of them are in like a three-legged race, but like all of their
Yeah.
legs are tied together, so they have to run in the same pace. If somebody's trying to run too fast, they're gonna pull them back. If it's too slow, they're gonna pull them up.
There you go. Except we don't pull up though, we only pull down.
Oh, we only pull down. Okay, so just overachievers, and everyone should slow down in the same way.
Exactly. Cool. So does everyone here have a good understanding of how the balancing works in the BMS? Okay. What about the thermistor expansion board? Were there any questions about that? Maybe I'll
So-
sorry, go ahead.
Are there 96 cells? And then we're just taking the temperature of every single cell?
So there's actually a total of 400 cells in the car
Oh.
because each one of these, if you see, it's 10S, 10P, which means that each line has 10 cells, and we have 10 of these. And then we have 4 of the BMS slaves. So each one is actually reading 100 cells. It's a lot of cells. It's a high voltage system, right? So we're mandated by the rules to read, I'm not sure exactly what the percentage is, but it's a little more than a quarter. So we need the 32 cell temperature readings from the BMS slaves alongside the 96 from the thermistor expansion board.
Oh, I have another question. Why is there 4 BMS slaves instead of just sticking it all into one?
Good question. It's because of the limitation of the hardware. Each one of these can only read 16 cells. That's just how the hardware is made. And so we would need to have, for symmetry purposes, we wanted to have each slave to be reading from the same number of cells. And so it made sense to use 4 of these, with each one reading 10 lines.
Okay, that makes sense.
Cool. Were there any questions about charger?
Another question on cells though. It says 10S, 10P. What does that mean? You said there's 400 cells, right?
Yeah.
Like, how are we actually reading 400 cells with this?
So you have, in the BMS slave, you have 10 inputs, right? So you have 10 inputs, and each input is reading 10 cells in parallel with each other.
Mm-hmm.
And then these 10 cells that are in parallel with each other are in series with 9 other of these lines of 10 cells in parallel. And so in total, if you have your first input, 10 cells in parallel, your second input, 10 cells in parallel, your third input, 10 cells in parallel, and so on. In total, you have your 10 inputs, you have 100 cells. And you know when you have 10 cells in parallel, their voltage doesn't get added onto each other. And so we're still reading 3.2 to 4.2 volts for each line, pretty much. Because voltage adds in series, but it doesn't add in parallel. And current is the reverse. I know you probably know this because you're power lead, but I just wanted to clarify.
That's why I asked the question.
Yeah, good question. I guess I'll say a couple more words about charger. For those who don't know, we found out that the charger, we don't really need to worry about like the specific algorithm of like what exact voltage needs to be sent to the battery pack at all times. We just send it the max voltage that we want the battery pack to reach and the current that we want to charge at. And so this simplifies things a lot for us because we just need to send the same message to the charger like every 1 second, just to let the charger know that the BMS master is still alive. It's kind of a heartbeat. We just keep telling the charger, all right, we want to reach 300 volts, charge at 20 amps. We keep telling it every second until we reach 300 volts. And it'll take care of all the nasty curves and all that stuff for us. All we need to do as BMS master is just do that passive cell balancing to make sure that the cells charge at the same rates.
I have a question about charger, kind of.
Mhm.
Is it possible to, before we start charging, to like read the total state of charge of the whole pack? And
Yes.
another question is, like, you know how like some cells can be like fully charged, others aren't fully charged. So how do you know the like total state of charge of the battery if like different cells are different voltages? You know what I mean?
Mm-hmm. We do actually, so we have, that is part of what the BMS master does, because we do need to estimate the state of charge of the battery from 0% to 100%. So I created an algorithm to do this. I can go over it. I actually have it here. Because this is actually a huge part of the BMS master. Because as the car is running, you don't want to shut off the car too early while you still have charge in the battery. So to do that, you need to have a reliable estimate of how much charge you have left. And you also don't want to over discharge the battery and hit under voltage, which could damage the cells. So we do something called Coulomb counting. I'm not really gonna get into the details of all the math of the algorithm because it might take a long time and be kind of complicated. But we're reading the total voltage of the battery pack as well as how much current the battery is discharging. And we take the two readings and combine them in this algorithm to give us an accurate estimate of what the state of charge is. And that's what we use to determine whether we need to shut off the car, or how close we are to finishing charging. I can go over the details of this later, but it's also in the drive for whoever is interested to look at it. Does that kind of answer your question, or was there
Yes,
something else?
totally. That's what I wanted to hear. Thank you. I also had another quick question. This might be a dumb question, but so the BMS slave, it reads the voltage of like 10 series, 10,000 series, right?
Mhm.
Why is it, if it's 10 cells, why is it 8 cell temperatures and not 10? I don't know, maybe this is really dumb.
No, it's not dumb. It's also just a limitation of the hardware.
Okay.
It just has 8 analog inputs. And so that's just all that we can read in terms of cell temperatures.
So do we not need to know the temperature of all cells, just like some? And that should be accurate enough?
That's why we have the thermistor expansion boards, because this gives us another 96 cell temperatures that we can read.
Oh, okay, gotcha.
And the rules only dictate that we need to read around 25% of the pack. So this meets that mark for our battery pack.
Perfect. Thanks.
All right. Quickly, just for the CAN to the dashboard and VCU in more detail. So the BMS master is a super essential component of the car. And so the VCU needs to know if the BMS master is okay. And so they share a heartbeat signal between each other every half a second or so, just to tell the other microcontroller that it's still alive. So that's one part of the CAN communication. Other than that, we also send over all the voltages that we're reading, all the temperatures. We'll send over if any specific faults happen. And we can send this to the dashboards to display the total voltage to the driver, display the average temperature to the driver, record this data for future analysis. I know Elena has been working on displaying this data to the driver, so she'll kind of have an idea of what we're trying to do. And so this part is mostly for the driver and for future analysis sake. But the main application of reading the sensors and all the algorithms is on the thermistor expansion board, BMS slaves, and the charger. Is there any questions about anything I've talked about so far? Cool. Sorry, somebody gonna speak?
I was gonna bag you on something. What's CAN? Is SPI and UART? Is that sort of
You
like
can watch Gabe's videos.
but like in a more general
Yeah, I can quickly go over, because these just look like some random acronyms for you guys.
Exactly, yeah. It's some random acronyms. What is it?
So without getting into the specifics of each communication protocol, this is just basically the way that these two chips or microcontrollers communicate with each other. And so the BMS slave wants to talk over something called UART, which is Universal Asynchronous Receiver Transmitter. And this is not something we picked. This is what the chip that comes on the BMS slave requires. And there's different advantages and disadvantages to each communication protocol. With UART, it's really simple. It's pretty reliable over short distances. It's only 2 lines, so it's not a lot of wires. And so this is the way that we communicate with the BMS slave. The BMS master has these different hardware peripherals that enable us to talk in these different communication protocols. And you can kind of think of it as each thing that we're talking to needs a different language, right? And so if BMS slave needs to talk over UART, the thermistor expansion board needs to talk over something called SPI, which stands for Serial Peripheral Interface. And this is just another way of laying out the ones and zeros that you need to send over. What's nice about SPI is that you can send big data sizes and it can be customized a lot. There's not really a standard of the type of data that you can send. And so it's pretty flexible in that way. And this is also not something we decided. It's just what the hardware on the thermistor expansion board requires for us to talk to. CAN stands for Controller Area Network. And this is super common in cars because it's very reliable against electromagnetic interference. So it's not going to be affected by noise. You can run it over long distances reliably. It's built in a way that you can have one line running through your car and having multiple things hooked up to that line and talking to each other. So you don't need a direct connection to the hardware that you're talking to. You just need to be connected to the CAN bus, and that will enable you to talk to different things. That's why here we have one CAN connection to both the VCU and the dashboards, because we'll just send a message on the CAN bus saying, this is the data, this is the address that we are sending this data to, and based on the address, it will deliver to the VCU or to the dashboards. For more details on the specifics of each communication protocol, I'd recommend just Googling it, seeing exactly what the specification is, watching some videos on YouTube. Gabe has a couple of really good videos explaining each of these on the Phantom channel. So I highly recommend just going over those. Is there any question about anything I've said? Andre, does that cover kind of what you were wanting to hear?
Yep. And I'm looking for the tutorial videos just to send to this chat so people can directly check it out.
Okay. Send it on the power channel, I guess, just in case anyone else wants to.
Yep. Cool.
Who wasn't on the team.
You got it.
All right. So we went over the hardware. We can go over the software as well. I'm not gonna go into a lot of details because I don't want to overload you guys with information. But you can feel free to look at this diagram in the power folder documentation and BMS master. But this basically just describes kind of the logic that the car is running on. Show of hands, who here knows what a state machine is? Elena, Alexis.
My hand's down.
Okay. Let's go over it really quickly, just in case. So, a state machine is not really like a specific thing to any programming language or anything. is just a concept that enables you to write code that is clearly laid out, that you can predict how it's going to behave based on the inputs it gets. So if you look at this diagram, you have two states, locked and unlocked. And based on the inputs to each state, and based on which state you're coming from, you will go to a different state. So for example, if you started in locked, and I hate hover zoom sometimes. Turn it off. Whatever. If you start from locked and you take an input of coin, you're gonna go to the state unlocked. And then if you're in state unlocked and you take another coin, you'll stay in unlocked. And then if you take an input of push, you'll go back to locked. So basically what this means is, based on, if we're thinking about the car, if you're in running mode and you're reading all the voltages, the car is moving, everything is good, and then you get a fault signal as your input, then we'll go from the running state to the fault state. So if we go back to this diagram, we have our running state here. And like, as I said, with a state machine design, you're able to really clearly lay out how your code is going to behave depending on which state it's in. So if we're in the running state, then this is what our tasks are going to do. And each of them has an inner state machine as well that also just helps clarify how we're having our logic flow from the different inputs that we're getting. And so if we're in running state and we get a fault, we'll go to the fault state, and this will trigger a different software flow. And if we are in running and then we start charging, then we'll do this set of things. And so it's just a concept that helps us make our code very modular. I'm not sure if that explained it that well, Alexis. Do you kind of get what I'm getting at?
Yeah, it gave me a good understanding. So there's three main states, and in each state there's more states. So is this state machine located in the BMS master?
Yeah, it's just like when I say state machine, this is, do you guys remember what a switch statement is? It was like a fancy if else, and you had like case, and each case would do something different.
I haven't used the switch statement yet.
But you kind of like, it's kind of like an if else statement, right?
Okay.
So let me pull up some codes.
What background is this?
Samurai Champloo.
That's
an
why
anime.
it's familiar. That's why it's familiar. I haven't seen that one yet.
It's pretty good. I used to watch anime. It's one of my favorites.
Ooh, I should go check it out.
Yeah, I should. It's been so long since I watched an anime. Like, he is.
Is it Code Composer the thing that's slow?
Yeah.
Ah, okay. Fair enough.
That now. Let's see if we have a state machine. Yeah. So state machine is a really fancy word for switch statement. Like we get our current state into the switch statement. If we are in BMS initialization, we'll execute this function. If we're in BMS operational, we'll execute this function. If we're in BMS critical fault, we'll execute this function. And so it just helps you really clearly define what you're gonna do depending on what's happening in the car. And so if we are in BMS initialization and we run this function, then we'll do all the stuff, initializing all the different settings that we want. And then in the end, we'll say that the state is now equal to BMS operational. And so the next time that we run this function, we're now going to be running this because our state is now BMS operational. And so it's not like a library or like a function. I mean, like a state machine is not a library or function. It's still plain C codes. It's just a specific way to lay out your codes. Does that make sense, Alexis?
Yes, thank you.
Mm-hmm. All right. Yeah, so now that we kind of understanding of how the state machine is applied in the codes, this is what we were actually looking at, the BMS slave state machine, because we have the outer main state machine that is running, and then inside the BMS slaves code, we also have another state machine to determine what we're doing based on the different states that we're in. And if we're in BMS initialization and we fail to connect 5 times, then we'll go to BMS faults. If we do connect, we'll go to BMS operational. If more than 3 cells are in faults, we'll go to BMS faults. And so, like, as you can see, it just makes it simpler to know exactly what's happening and why it's happening. Feel free to look at this diagram and shoot me questions if there's anything that doesn't make sense. But yeah, this is all just fancy switch statements and if-else statements, nothing more.
If you do
Alright.
detect a fault, how do you guys get out of the fault state?
Right now, all the faults, because we prioritize the driver's safety. So right now, BMS faults, if it's something to do with the battery, then we'll just shut off the car. Because like we just want to make sure that the battery is not going to explode, our driver is going to be safe. But that is something we are looking at, kind of determining the reaction to different severity of faults. And that's something that still needs to be done. It's one of the tasks. So if it's something like you've lost communication for like a couple seconds, or you got like a crazy value, you're reading 500 volts on one cell because something got messed up in the communication. We want to handle that and not just shut off the car, but wait and see if the problem stays, then we can shut off the car. So we'll probably have a critical fault states and then like an intermediate fault state where you're just kind of keeping track of if anything else goes wrong, then we'll just shut off the car. But that's a good point. Is there any other questions about the software?
So I'm trying to find where I can access this thing in the Google Drive, but I can't seem to find it.
So if you go to Phantom Engineering, Power, Documentation, and then BMS Master Firmware.
Okay.
And then you'll find all the diagrams that I've used today. I'm just gonna like, no, this is gonna be on, I was gonna check the elections, but this is recorded, so I'll just do it after.
You don't want it. You don't want that recorded.
It's okay, this is good. This is like, I haven't thought about it that much, so.
Yeah, no, it's not. It's on your mind. How's everyone doing though? Everyone still keep going for more? This is pretty interesting to me. So
I can wrap up. I just, there's not much left. I'm just gonna go over just kind of what's left to do. Yeah, this is the BMS tasks, just kind of everything that we want to complete before we can say that the BMS master is ready to be put in the car. So the charging is a big part of that. State of charge, while a lot of work has been done on that, is still kind of a work in progress. Just because of some minor things that we need to do. Charging as a whole, Elena has been working on that a little bit. And we want to start integrating that into the main codes. We want to handle faults better. This is also a big part that Emma mentioned. Balancing has still not been done properly. It's kind of like a first version of it has been written, but we need better logic for when to enable it and disable it. More documentation for how we're handling faults. I think Junaid started a document on this, so we're going to be adding more to that. CRC fault handling is just basically a way to handle errors in communication and just to verify that the messages are being sent correctly. Watchdog is something that needs to be done for BMS Master. And what this is literally just a hardware component on the BMS Master that's tapping the code and saying, are you still alive? And if it's alive, it'll, it's called kick the watchdog. And so you need to kick the watchdog every second, or else it will reset the microcontroller. And this is just to make sure that your code hasn't like broken at any point and frozen. It'll make sure that your code is running properly. And then CAN is kind of, Zinglu has done a lot of work on creating like how we're going to be sending the messages, but we still haven't like defined when we're going to be sending the messages or how we're going to be pulling this data from each sensor and then formatting it and sending it over. So this is also a big part that needs to be done. Our main repo is on GitHub, the BMS firmware repo. I've been doing a pretty good job keeping track of tasks on GitHub as well. So this is all the stuff that's been done. This is what I was working on currently. And these are things that are still to do. And it's mostly the same as the diagram that I just showed you guys. So yeah, when you guys are ready to start working on stuff for the BMS firmware, you would clone this repo and work off of the develop branch. And you would just branch off of that to implement whatever feature you wanted to do. Like if you wanted to integrate CAN, you'd work on the integrate CAN branch and so on and so forth. And then inside that is the actual Code Composer Studio project. And for those of you who have used it before, you just import the project and then you just start working on the code. It's just text editor. There's a tutorial on the firmware firmware repo. If you go to the wiki, you'll find some getting started information. I find that it's pretty good to run through these tutorials and next steps in learning, just to kind of get familiar with Code Composer Studio and Halcogen. And for those of you who don't know, Halcogen stands for Hardware Abstraction Layer Code Generator. And it just automatically writes a lot of the really low-level C code that's interacting with the hardware, just so we don't have to go through all the work to do that. And it's able to do that because like that really low level interacting with hardware is going to be the same for any project that you're doing. It will just depend on which microcontroller you're using. I don't think I'm doing a great job of explaining it, but I guess, Andre, are we going to be able to get launch pads for Emma, Elena, and Alexis?
If we have spare ones. We need to go.
Have a launch pad.
Yes. Yeah, we need to go double check with that. But as of right now, I'll finish up with your lesson. But eventually, we should be getting launch pads for them, and checking up
Okay.
on other people's launch pads.
That'd be good. Because then you guys can run through these projects and get an idea of how to use a microcontroller. I'd say for before that, just working on some C concepts. I think the ones I sent Alexis here, just brushing up on what pointers are, structs, timers, interrupts, just researching into those, maybe applying those in some projects in C, just some example code just to get familiar with how it works, because we are working with embedded C, but C is the same no matter what platform you're running it on. And so for the syntax and these concepts, you can apply them whether you're running it on a computer or on a microcontroller. So it'd be really good to just look into these, try and get an understanding of how they work, and even maybe looking through the code in the BMS firmware repo and seeing like how we implement these things in our codes. And I'm sure you guys are gonna have a lot of questions about that. So feel free to, like, if you see something and you don't understand it, send it on the Power channel, and I'll try my best to get back to you. Cool. Is there any questions about anything I've talked about today?
Is the Launchpad a microcontroller?
So that is a good question. The microcontroller is actually just the chip. Yeah, if you can see on Andre's screen, that little black square.
Oh, okay.
This is what the microcontroller is. And the whole thing is the PCB or the launch pads. And so the microcontroller has a lot of the communication protocols and different things inside it. And these are all on each individual pin. And the pins are broken out into headers that you can actually connect to. Yeah, good question.
Thank you.
Cool. Anyone else have any other questions? Any questions about next steps, about what each of you guys are going to be doing next?
After this, would the lesson be ending here? So just so we could finish the.
Yeah, we can stop recording.
Cool.